Hello class. We are going to begin our conversation about electronegativity and how that fits into the three-dimensional shape of molecules, and what that leads to is solubilities and all kinds of interesting things like intermolecular forces, and describes a whole bunch of why things do what they do in the realm of chemistry. So I'm going to start in on the conversation about this term right here, electronegativity. Electronegativity is a measure of the attraction an atom has for electrons. Atom has for electrons. So it may or may not make sense to you in terms of the attraction atoms have for electrons. We haven't talked too much about this octet rule and how atoms like to have an octet in their outer energy level. They like to have a full shell or subshells, so that makes them stable. I'm going to just kind of cruise on over here to a table that I gave you in class, or you have as a reference page, and this is a periodic table where essentially what you're looking at is every one of these numbers on the bottom. They have the elements there, but we just have the electronegativity, which is again that measurement of attraction that an atom has for electrons. You might notice that when we cut that periodic table into the metals over here and the non-metals over here, we can see that for the most part the electronegativity of the metals is low. I'm going to just say En is low over here. And that's because metals tend to give away electrons to achieve their octet. And I'm just going to write 8 for octet. And the non-metals, you can see that relatively speaking, the electronegativity is high. So basically the electronegativity of non-metals is higher because they gain electrons to achieve an octet. And you can kind of see that. Okay. One of the things you'll notice is these guys, for the most part, those noble gases over there, with the exception of these guys down here, have they don't even have an electronegativity because they don't want electrons. They have achieved stability and they have a full octet. They have stability and they don't want electrons. You'll notice that the electronegativity in a group, with the exception of hydrogen, because that one's weird, but basically it goes down as you go down the family, and that's because the radius of the atom gets bigger. So there's all kinds of reasons why these numbers are what they are. You'll notice that, again, it goes down as you go down the family because of the size of the radius. And the electronegativity as you go across the periodic table in terms of the periods, it goes up, and it all focuses on this element right here. Fluorine has the highest electronegativity. Now, what that means to us is we are just going to be interested in which atoms want electrons more. And so we can say that the metals are willing to get rid of electrons and the non-metals are going to want electrons. And when we look at our bonding between atoms, we're going to contemplate this concept of electronegativity. So once again, electronegativity is a measure of the attraction an atom has for electrons. Okay? Why is that important to bonding? Well, it turns out that this unequal sharing of electrons leads us to polar bonds, and it can lead us to this idea of a dipole. So let's chit-chat about a compound called CH4. This is methane, CH4. And it has carbon in the center, it has hydrogen, it has hydrogen, and it has hydrogen. We would call this a tetrahedral molecule. Its central atom has 4 things attached to it, and each of them are atoms. We know about the bond angle is being that 109.5, and we know this is a tetrahedral shape. So there's all kinds of stuff we know about this. Okay. It turns out when we look at the bond, the type of bond that exists between these atoms, we look at the electronegativity. And we look at the difference in the electronegativity. And so when we look at the difference in the electronegativity, if you have the electronegativity that is greater than 0.5, okay, we call that a polar bond. or greater than or equal to. And if we have electronegativity that's less than 0.5, we call it a nonpolar bond. And what that basically means when we say polar is the electrons are being sort of drawn away from atoms and they're drawn to the other more electronegative element. If we say that it's nonpolar, basically we're just assuming that the distribution of electrons, the desire the atoms have for electrons is about equal, and so the electrons sort of have this uniform surrounding of the atoms. Okay, so when we look at this particle, this bond between carbon and hydrogen, if we just look at that bond between the carbon and hydrogen, we're going to look up the electronegativity of carbon and the electronegativity of hydrogen on our chart. So we have to scroll over here and look at hydrogen. So hydrogen's got a 2.1 electronegativity and carbon has 2.5. Okay, so when we go back to our bond, we're going to look at that difference. Whoops, yes, we're going to look at that difference. And so we know that hydrogen has a 2.5 electronegativity, carbon has 2.5. When we subtract those from each other, we get 0.4. And when we fit that into our difference, essentially we're saying that this must be a nonpolar bond. And that's true. So what that means, again, is that when the electrons are sort of interacting in this covalent bond, the sharing of electrons between carbon and hydrogen, they're sharing fairly equally. Carbon is wanting the electrons a little bit more than hydrogen, but for the most part, we're going to call that nonpolar. And so what happens in this molecule is those electrons are going to be distributed equally. Each of these bonds, 1, 2, 3, 4, is the same, right? And they're all nonpolar. And then basically this we're going to get to in a minute is a nonpolar molecule. Okay. When we have a bond between, let's say, oxygen and hydrogen in a water particle, and we know that water is bent because it has 2 non-bonding electrons and 2 atoms attached to it. We have this bent molecule. When we just go and scrutinize the bond between oxygen and hydrogen, again, we look at their electronegativities. Hydrogen we just looked at was 2.1, and when we scroll over, it's hard for me to scroll on this thing. I have to really scroll. It's changed. When we look at oxygen, if you look at it, it's 3.5. It has a very high electronegativity, a very high desire for electrons, partly because of its radius and partly because it's really close to being a noble gas. And so when we go here and look at oxygen's electronegativity of 3.5, when we subtract that, we get a difference of 1.4. And when we look at that difference, that fits in the category of being a polar bond. So what that means is oxygen is wanting the electrons more than hydrogen. And so in that bond, the electrons are going to kind of swarm around the oxygen and not as much as the hydrogen, because the oxygen is pulling those electrons towards it. That's what when we talk about a polar bond, this atom wants the electrons more, and so basically the electrons are going to hang out closer to the hydrogen. Okay, one way to talk about a polar bond, is to talk about how it has a dipole. Okay, so when we determine the dipole, we've just done that. When we determine the dipole, we're looking at the difference in electronegativity, and we have these cutoffs of 0.5, less than 0.5, no dipole, greater than 0.5, then we have a dipole. We have an unequal distribution of electrons. So when we look at a dipole, we can do this 2 ways. We can do a little cursive D where this side of the bond is positive because the electrons are missing, and this side of the bond is negative because the electrons are hanging out by it. So that's one way. So we can show a dipole with this cursive positive and negative, and we'll make sure that the negative side is the more electronegative element. So that's one way we do it. Another way to draw a dipole, so that's our first way. Our second way to draw a dipole, okay, is to actually draw an arrow. So when I look at the bond between oxygen and hydrogen in this case, we know that the electrons are hanging out around the oxygen more. So we're going to draw a bond dipole. So make sure we understand this is a bond dipole, and that's going to be important in a minute. Okay, and the bond dipole points in the direction of the more electronegative element, so it points towards oxygen, and then there's a convention of a little positive end. Okay, so it's an arrow. It points in the direction of the more electronegative element, points towards more electronegative element, and it has a little positive side to it, so we draw it like that. So this is a bond dipole, okay, bond dipole. So that's basically the concept. So we want to understand electronegativity, this unequal attraction that atoms have for electrons when they're bonded together. So when we think about the bonds in a molecule, we have to contemplate the difference in the electronegativity, and we have sort of a scale that helps us decide if it's polar or nonpolar. I did that backwards, polar or nonpolar. Once we've decided that it's polar, the third thing we have to do is we have to indicate the bond dipole, or we at least have to think about the bond dipole. Okay, and again, I'm making a big point that bond dipoles are going to be different than net dipoles, and we'll get to that in just a second. Okay, so 3 things. So the next piece of this is putting this all together in the 3-dimensional space of these molecules. And so I'm going to skip over, and we're going to talk about those 3 molecules that we just did, those 2 molecules that we just did, and we'll add another. So I drew out methane for you, CH4, right? And I would encourage you guys when you're doing this to first do the Lewis structure, right? Like I taught you earlier. And then think about the 3-dimensional shape of the molecule. And then you're going to analyze the bond to determine if it's polar or nonpolar. And you'll want to, I guess I should put bonds as plural. And then once you think about the polarity of the bonds, then you're going to think about the net dipole. So that's what I'm going to cover right now, the net dipole. So the net dipole basically is a manifestation of the bond dipoles within the geometry, the 3D geometry, right? Okay, so methane, we've decided, we've done the Lewis structure, we know the 3D shape, and we know basically that it is tetrahedral. Okay. We know that basically none of these bonds are polar, and therefore we don't have to indicate any dipoles. And ultimately what it means is the difference between the carbon, the 2.5 and the 2.1, indicates there are no bond dipoles. Okay, and then basically within the 3-dimensional shape of this, that means that there is no net dipole, because nothing is sort of pulling in opposition. And ultimately, that means that the electron distribution is symmetrical, which is the really important part. The electron distribution is symmetrical. That's really important because that means this is a non-polar molecule. Okay. So that's the best case scenario. No bond dipoles, no net dipole. We have a nonpolar molecule. Okay. And again, remember that polarity has a lot to do with solubility, right? So polar dissolves polar and nonpolar dissolves nonpolar, but nonpolar and polar don't like each other. So we talked about water a little bit, H2O. If we think about, again, the Lewis structure, the 3-dimensional shape, and we talk about the bonds, we've done that already, so I want to kind of look at that with you. So we know that oxygen is the central atom. We know hydrogen is attached, and we know there's these lone pairs. We also know, because we already looked at it, that this is 3.5 and 2.1. I have 2 polar bonds, and we drew those dipoles, the dipoles in here. There's a pull of the oxygen from the hydrogen in the direction of oxygen, and there's an equal pull of oxygen from hydrogen in that direction. And ultimately, that means I have 2 polar bonds, right? That the oxygen-hydrogen bond is polar, and there's 2 of them. So that's our bond dipole. When we think of our net dipole, we have to think about how those 2 those two bond dipoles are interacting in the three-dimensional shape. And so basically this is a hard one, but there is a net dipole for this particle, and that's because they're kind of pulling in this direction. So collectively the two bond dipoles are pulling and creating a net dipole in this direction. So our net dipole is the manifestation of these two polar bonds acting in the three-dimensional shape of this bent structure. So when we look at the electron distribution, we get a lot more electrons over here, and we get not very many electrons over here. This makes this part of the molecule negative over here, and that makes this side positive, and that is a polar molecule. So you have an unequal distribution of electrons. Okay, where the electrons hang out, the electrons converge basically. Convergence is the negative side of the molecule. Okay, negative side of the molecule. Okay, so that's a huge idea. Okay, so now we have a nonpolar molecule, we have a polar molecule. I want to show you one more example, which is kind of crazy, but I'm going to show it to you anyway. I want us to think about carbon dioxide. Okay, it's a molecule that's really important. We exhale it in the process of metabolism. If we did the Lewis structure like I'd like you to do, we would add up 4 carbons. So I'm going to start at the very beginning. We have 1 carbon, and it has 4 electrons. We have 2 oxygens, and they each have 6 electrons. So I have 12 plus 4 makes 16 electrons. I know that carbon is going to be my central atom because it makes more bonds than oxygen. I'm going to use up 4 electrons to connect oxygen and carbon together, and I'm doing it with symmetry in mind. So I've used up 4 electrons. I have 12 electrons left. I'm going to try to give those 12 electrons to the atoms that want an octet. So I'm going to do it like that. And then I'm going to stop back and look to see and notice that I have 8 electrons around oxygen right there. And I have 8 electrons around oxygen right there. But when I look at the carbon, I notice that it only has 4. That's not good. So what I'm going to do is, as we went through our Lewis structure laws, I'm going to erase these 2 electrons and put them in between to make a double bond. I'm going to do the same over here to make a double bond. And then I'm going to see again that now oxygen, by sharing these electrons and these electrons, both oxygens get 8 and carbon gets 8. So when I look at that and clean this up a little bit, you see that I have 2 bonds between the carbons and 2 lone pairs on each of the oxygens. So Lewis structure. The second thing I ask you to think about is the geometry, the shape of the molecule. So you might notice that this is a linear molecule, and that means that this angle between them is 180 degrees. Okay. Third thing is to note bond dipoles. So we ask ourselves the question. We look at the electronegativity from the chart. So I'm scanning over here. I think it's on the back side now. Where is it? There it is. We're looking at carbon and oxygen. We know that carbon is 2.5 and oxygen is 3.5. So we're going back to, let's see if I can make it happen. There we go. So we know that carbon is 2.5 and oxygen is 3.5. When we do that subtraction, we find that that's a difference of 1, which qualifies as a polar bond, which means I have a bond dipole in that direction, and I have a bond dipole in that direction. So I have 2 polar bonds, right, in the direction pointing towards the oxygen. But here's the weird part about it. When I think about it in the geometry, so I'm asking, is there a net dipole? That's my next question. And the answer is no. There is not a net dipole because these 2 dipoles, the dipoles actually cancel each other out. It's like a tug of war, so each of them is pulling in the direction as the other with the equal force. They're pulling in opposite directions in this linear space. And so ultimately what that means is there's this symmetry about this. And so polarity has a lot to do with symmetry. So this is kind of a crazy idea that I have two polar bonds. I have two polar bonds, but I have a non-polar molecule. Okay, I have a non-polar molecule because basically those dipoles cancel each other out. So that is a huge idea, and that's where we're going to go with this. So I think I'm going to go back to my pages here and make sure that I've said what I wanted to say in this video. Okay, so a couple of questions there, making sure that those can be answered. And then I'm going to have you guys work on the problem set here. So kind of applying some of these concepts of geometry and polarity. And I will go ahead and give you those answers. And as I upload that content for you, you can check those answers. Thank you so much for listening. I'm hoping you have a great day.